Okay, so today we're going to be looking at finding the key features of a graph. It's important, particularly on this course, to use technology to find our extreme points and asymptotes. So let's have a look through what we're learning today. So a bit of vocabulary first. We can talk about extreme points. So an extreme point can either be a local extreme point or a global extreme point. We have two different types. We have local extreme point and global extreme point. You have synonyms that you might see used. I'm including them here. So typically in our IB course, we're going to be using local and global. We'll use these words. These are the words we will use primarily. Relative is a synonym for this, and I'm including this one for those of you who are taking PSATs or SATs. This is the vocabulary that they might use on American examinations like that. So relative extreme point or local extreme point, absolute extreme point or global extreme point. So an extreme point is a point where the curve reaches a maximum or a minimum. An extreme point is where it reaches its extremes. You can find an extreme point when a curve changes from rising to falling or from falling to rising. So if we go rising and rising and we start falling, it means we've gone through an extreme point. We've gone through a local maximum. If it keeps falling and falling and then starts rising, we're going through a local minimum. So in this particular case, we are going to have a local maximum here. And we're going to have a local maximum here. This is where the curve goes from rising, 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 and then it starts falling again and creates a local maximum. We're also going to get a local minimum here, where the curve goes from falling to rising. However, we have one more local minimum. Listen to this bit, because this bit is where it gets a little tricky. So this is where the graph, in one interval, reaches its lowest point. So we can see that the graph reaches its lowest point here as well. Here we have a restricted domain. So if we look at the domain of this function, the domain of the function that we're looking at here starts here at -4. So our domain is that x is greater or equal to -4. Because -4 is included in the domain, it means that this point here is included in the graph, which means this point here is a local minimum point. Now, at the other end, notice that we don't have, the domain is not restricted at the upper end. It continues to infinity, which means it continues endlessly. We can see that by the shape of the graph here, where it comes down and it has an arrow on it. It has an arrow. This means it continues endlessly, which means in this side it will not reach a minimum, because whatever value it reaches, it continues on after that and reaches a lower value.
So it just keeps continuing down and only down.
Yeah, infinity is not a number. It just keeps going down towards infinity. We always talk about it going towards infinity, never being equal to infinity. So it will just keep going down and down and down, and it will never get there. It will never stop. So it will never reach a minimum. It just keeps falling endless. So here we see it going down. So we can't say that it has a local minimum here, because it just keeps going down, and whatever we say it gets to, it goes lower. So the local minimums, we always reference key points on a graph by the domain. Pretty much everything, you're always referencing the x value. Other than when you're talking about the value of the function, when you're talking about y values in the range, everything else, say it occurs at, and then you give the x values. This is the independent variable. So we use this to reference where things occur. So the local minimums occur at x equals -4 and x equals 0. So we have two local minimums. Where do the local maximums occur? In the yellow. Can we see the x coordinate for these ones? What would they be?
2 and 3.
-2 and 3. Okay, so these are the local minimums and the local maximums. Now the idea of a global extreme point, this is where the one local which is smaller than all the others, or the one local which is larger than all the others. So the global maximum is the one local value which is larger than all others. What would that one be? So here at x equals 3, we have our local maximum. So the the absolute maximum, the global maximum, or absolute maximum, is at x equals 3. Now, what is the absolute maximum value? What is the absolute maximum value? Not where is it at, what is the value? What is the largest value this function makes? Alexander? 2. The y value there. So the absolute maximum is 2, and this occurs at x equals 3. What about the absolute minimum? Now this one is tricky. So you might be led to think it's going to be here. Yeah. Which doesn't exist. So we use D and E. Does not exist. There is no absolute minimum, because whatever we say, there's a number smaller than that one. Infinity is this endless concept. So if it just continues in one particular direction, it would not have an absolute minimum. Okay. Have a go, see if you understand. Work together with people next to you. Have a go at these 2 questions. Just going to pause the video for 5 minutes on this one. Okay, so we've had a look at these ones. We need to find where the relative minimums are. The relative minimums is going to occur here. We only have one relative minimum. We say that it is at x. We say that it is at x equals minus 2, and this is how we reference it, so minus 2. We have 2 relative maximums. We have one relative maximum occurring here, and one relative maximum occurring here. So this one occurs at x equals minus 4, and this one occurs at x equals 3. So we have one at minus 4, and we have one at 3. Absolute minimum. We don't have an absolute minimum because the function will continue to fall in this direction. So this one does not exist. Absolute maximum, it's going to be this one at x equals 3. It's going to be this one over here. And the y value there is 2. So this one is 2. So if we're talking about the end behaviors here of this graph, when we're talking about the end behaviors, at the left-hand side, the left-hand end behavior, we reach a minimum, a maximum point here at x equals 4. But if we wish to talk about the end behavior in the other direction, we would use a phrase such as x approaches infinity, then y approaches negative infinity. So if you wish to talk about the end behavior, we can use a phrase like this one: as x approaches infinity, then y approaches negative infinity. And this is why the absolute minimum does not exist. So here on the second one, where do we have the relative minimums? What are the 2 coordinates? Let me take somebody else.
Negative 3 and 3.
Negative 3 and 3. Where do we have the relative maximums? Here. 0 and 5. Yeah. 0 and 5. Any other one? Negative 4. So we have 2 the maximums at each, one maximum at each end point. What is the absolute minimum? What is the absolute minimum? Let's have somebody else.
Minus 3, x minus 3.
The absolute minimum is going to be here, minus 3. And this occurs at x minus 3. What is the absolute maximum?
4 at the top of that equals 5.
This is 4 and it's occurring up here. X equals 5. Excellent. Okay. So consider the function f of x drawn here in the graph. How many turning points does f have? How many turning points? There's a little bit of vocabulary here. So our key vocabulary on this one is turning points. So turning point is a way of classifying extreme points. Extreme points. So how many turning points does the function have? 3. In what interval is the function rising? So rising, this means that the function is going up. So in what interval is the function rising? We can talk about this interval here, and we can talk about this interval here. Now, when we talk about it rising on this course, we are going to be doing it from a derivatives perspective. There's 2 ways to talk about a function rising, defining what is a rising interval. If you want, I'm going to explain it a little bit. You have a strict definition. Now, a strict definition of a rising interval will include endpoints, because technically, a function cannot be rising at any single point. A function can only be rising over an interval, because in order for it to rise, the x values have to change so that the y values change. It's not rising at one point. At every single individual point, it's still. Rising is an idea of what happens to the function as you increase the x value. Does the function go up or down? So it's looking at over an interval, is there a change? So this means you would include an endpoint in a strict definition of what is a rising function. But on this course, they're going to do it from a derivatives perspective, which means we're not going to include the endpoint, because at the endpoint, the gradient is going to be 0, and we're going to say that the function is neither rising nor falling at the extreme points. So all that means is, where is the function rising? We can clearly see here. So the function is going to be rising from -5 up to, and in this definition I'm not going to include -3, because I'm going to say at -3 the function is neither rising nor falling. But this is from a derivatives perspective. So technically, if I'm doing it from a derivatives perspective, I shouldn't be including -5 either. I want to explain that one, but there's no derivative at an endpoint of a function. We're going to see derivatives next at the end of the year.
So when we do the rising, we do it based off the x value instead of the y?
Always, always. Whenever you're referencing parts of a graph, you're always referencing the x values. So it's rising in this interval, and we're going to say that it's rising in this interval as well. From -1 up to 2. What is the minimum value of f? What is the absolute minimum value? -5, yeah. So -5 is the absolute minimum. When does the function reach its maximum? So here it's talking about when the function reaches its maximum, not what is the maximum. So notice that there's a difference in the wording of these 2 questions. The first one is, what is the minimum value? And this one says, when does it reach its maximum? So this one says, what is the extreme value? And this one says, when does it reach its extreme value? So in this case, when is an x value. So when does it reach its maximum value? This one is x equals 2. So what is the minimum value? That's -5. What is the maximum value? That's 3. When does it reach its minimum? At -5 and 4. When does it reach its maximum? At x equals 2. So,
And what interval is that for? For the second one, where you put -1, why didn't it start from -3?
because, so the interval where the function is rising is this bit of the graph and this bit of the graph. So when I give my intervals, I'm shading these 2 areas of the graph. And these are the intervals and the regions of the graph in which the function rises. And the other intervals are the regions of the graph, the function that does not exist, but is for.
The minimum value is that's the y value?
Yes, that's the y value.
And then for the interval where we put the inequality, are we going to put the equal sign or?
We're going to leave the equal sign off on this course.
So for those intervals, are they always like vertical?
They would have y's in them to make them horizontal. Where, you mean how I shaded the graph?
Yeah, like would it ever be a horizontal line?
No, not whenever you're referencing where things occur on a graph, you're always referencing the independent variable, the x variable. So pretty much most questions is looking for the x value. Whatever the concept is that you understand that it's asking after, the majority of them will be x values. Only when it comes to what is the value and what is the range, you tend to talk for the horizontal asymptotes, we talk about the y values. Okay, next piece we want to do is to take out your graphing calculators in your hand. Everybody has to have their graphing calculator for this one. This is a graphing calculator skill. So what we're looking at now in this next one is a typical skill, which is we're given a function, we've done this before, and we are going to try and draw all the key features of the graph. So I'm going to list the types of things that you need to include in your graph. You're going to use your calculator to aid you. You have to get the correct, so things to include. Things to include. Number one, use a pencil. Draw a sharp line. So use a pencil in case you get it wrong. You've only got one set of graph paper on this one, usually when you're drawing this type of stuff. Make sure you always have a pencil when you're taking an exam. Use a sharp line. Don't do this. Don't do this. It has to be a clear, firm line, like this one. So you also, there are going to be key elements that you have to include. Number one being the correct shape. If they have them, axes, intercepts, these should be correctly drawn. And labeled. So notice on this question, we are going to we're going to draw the graph on this one. So axes, intercepts, correct shape, extreme points. If they have them, asymptotes. Asymptote should be drawn with a dotted line and a ruler. Asymptote should be labeled, e.g. x equals 3. The correct shape at endpoints. If there's a restricted domain, include endpoints. This will also give you a y point. If there's a restricted domain, you can see the endpoints, asymptotes, extreme points. If there's more than one graph, obviously intersections. Can't remember them ever asking to do 2 graphs, but intersection. These are the things to include. So take a minute now with your graphing calculator, graph it, find the information, find the key information, plot the key points first, then try and get your sketch to go through those key points. Use a ruler if necessary. You can always grab one from my box at the back I'll give you 5 minutes for this one. So we're trying to sketch the graph. We can see how the graph looks on this one. We don't have too much information to sketch on it. We don't have any extreme points. We do have some asymptotes defined. So we can see that there's an asymptote around about here, and we can see that there's an asymptote around about here. You can see there's two vertical asymptotes for this one. Now, I'm not quite sure what they are, but I can have a guess at it. But let me show you a technique where you can see, I think there's an asymptote here, and I think there's somewhere around here. If you want to locate the exact value, go to the calculator page. And what we're going to do is if we look at the function, look at the denominator. The denominator is x squared minus 4. We're going to set that equal to 0 and solve it. So you want to take the denominator. So we just switch. You want to take the denominator, which is x squared minus 4, set it equal to 0, and solve. So this is a polynomial. We'll use the polynomial root solver to solve that one, because there's going to be more than one solution, and nsolve will only give you one of them. So we're going to use the polynomial solver. No, press the wrong buttons. We're going to do menu, algebra, polynomial tools, find the root of a polynomial. It's second degree. Coefficient of A is 1. The coefficient of B is 0, that's why we can't see it. And the coefficient of the number at the end is minus 4. So we'll put it into the polynomial root solver. It will solve the equation for us, and it will tell us. We can see it's probably minus 2 and 2. If we want to confirm it for any reason, then solve the denominator equal to 0, and it will tell us that. So we need to put these bits in first. Always take a ruler to draw your asymptotes and start with asymptotes first. So we've got one asymptote here. We have another asymptote here. Then you need to make sure your asymptotes are labeled. So this is x equals negative 2 and x equals 2. Now, if we look back at the graph, do we have a horizontal asymptote? So a horizontal asymptote can also be found algebraically. Now you're going to get a horizontal asymptote if the polynomial in the numerator and the polynomial in the denominator are the same degree. They're both x squares. So if they are, take the coefficient in front of them and divide them. So let me show you how to do this one. So we have x squared plus 4 over x squared minus 4. This is approximately going to be equal to x squared over x squared, which is equal to 1 over 1. I'm looking at the number here and the number here. They're 1s. So 1 over 1, this will give you the horizontal asymptote. It's y equals 4. And we can see that visually as well on the calculator. So take the number at the front, the coefficients of the lead coefficients of each one, and divide them. Now, if the exponents are not the same, if the one on the top is bigger than the one on the bottom, you'll see it will just rise up to infinity or fall down to infinity. If the one on the bottom is bigger than the one on the top, then you'll see it will go towards 0. It will go towards 0. So you only get a horizontal asymptote other than 0. So you only get a horizontal asymptote when they're the same, and you divide these two. Or you'll get one that is 0, and that's when the one on the bottom has a greater exponent than the one on the top. Right, so we found our key asymptotes on this one. Let's sketch that one in. This one was here. So start by drawing your asymptotes. Always start with the asymptotes. You're drawing with the ruler, and then you're labeling them. So this one is y equals 1. Next, what you have to do, we do have an extreme point. We have an extreme point here at the y-intercept. So plot your key points. This point here is important to us. It's at 0, 1. Typically, I would label them 0, 1. There are no more axes, intercepts, nothing else is of interest. So now you can draw with a smooth line, show your asymptotic behavior, which means it has to approach the line without touching it. It's going to go up like that, come up to there, and then it's going to come down like that. So this part of the curve should look like this. You don't have to particularly be too accurate with this one, but what you might want to do is you might want to find a point somewhere over here. So you could just trace a point or two to help you line it up. So you could use menu trace. I'm going to trace a point around about x equal to 3. Let me see where it is. So I'm going to type x equal to 3, press enter twice, and it goes through about there. I'm going to try over at the other side. I'm going to type in -4, see if that's a better number. Get one in over here. No, that's not a better number. So it's going to go through around about 3,2.6 and -3,2.6. These 2 points. I'm not going to label these. I'm just using them to help me get a good shape. And then my curve looks like this. So now I have a good shape. This is a good curve. This is a good curve.
So with that point, there's 0.1. Wouldn't that be a local maximum?
Sorry, it's 0, -1.
Wouldn't that be?
Yeah, it would. It's a local maximum and an axis intercept.
Would that be an extreme or not?
No, it would be an extreme point. It's a local extreme point. It's not going to be a global one. This one doesn't have any global extreme points.
So we would mark the global extreme points and then pass for the local.
We would mark all of them. We would show all extreme points. They're important to include. But this curve is just going to keep rising in different directions.
So would we have to like drop down the?
Should we write like local labels?
No. So just draw it clearly and label it. You don't have to identify it. If they want you to identify it, that's going to come in a later question. They're going to say, what is the local maximum? Well, it might come in an earlier question to help you with the sketching. Typically with this type of a question, it might ask what the range of the function is. So after you've sketched a graph like this, to test your understanding, it might be what is the range of the function. I think we had one like that on the last exam. So the range of this function is quite difficult, isn't it?
Yeah.
So the range is going to be coming from -infinity up to -1, and then from 1 up to infinity. So the range of this function is an interesting question. I know I've asked that a few times, and the range would be -infinity up to and including -1. So we have to include -1. But because this is an asymptote, we're going to not include 1, and we're going to go up to infinity. So here's a great question to ask about this type of a graph, is what is the range? Because we have a gap in the middle of it. We have a gap in it.
So when we're doing the inequality from -infinity to -1, we don't do like equal to like less than.
We only have an equal to for the -1. The curve goes through 0, -1. And the rest of them, because they're asymptotes, it never reaches those points. And because they're increasing and decreasing without bound at the either side of the asymptotes, we don't get to infinity either.
So,
Are they not considered?
Good questions, everyone. They are, so if you want, you can draw a little arrow here as well, here as well.
what about the domain? Because, for example,
So the domain is going to be all x other than the 2 vertical asymptotes. So if we wanted to do the domain of this one, the domain is probably best specifying just what it's not. So x is not equal to plus and minus 2. I'll do this. X is not equal to plus and minus 2. Otherwise, x is any real number. Okay. Have a go at sketching this one. Have a go at sketching this one quickly. So we're not going to be drawing the axes on this one, we're just going to sketch it. So we won't use the grid, we're just going to sketch it. We're going to identify where the asymptotes are. We have a horizontal asymptote, we have a vertical asymptote. Let's have a go at sketching this one, Alexander. Let me just pause a second. We are sketching this function here. Let's have a little look at the function. So if we put it into the graphing calculator, it's going to look like this. We're going to need to extend the axes a little bit here. So I'm just going to put this one up to 20. We get a better feeling for the shape. Make this one a little bit, not quite as much. I'm going to go down to minus 15. So we can see the whole shape of the graph now. We can see it's going to have a 0 at x equals to 0, but let's make sure we find that one. So analyze the graph, find the 0. We want that one. So we can see it's got a 0 here at the origin. Next we need to find the horizontal and vertical asymptotes. So what I've recommended we do is we take the denominator, which is x squared plus 5x plus 6, set it equal to 0, and solve. When we solve this on the calculator, we can use the polynomial root solver. We say algebra, polynomials, find the roots. It's a second degree function. We've got 1, tab, 5, tab, 6, enter. And then it's going to give us minus 2 and minus 3. So if we look at the graph, which one is it? Is it at minus 2 or is it at minus 3? So I might just go to graph, window, and relation. And I can enter in x equals minus 3. And I can see that the horizontal asymptote is here. If I was to put in one at enter relation, if I put one in at x equals minus 2, we'll see that this isn't an asymptote here. We can see that this isn't an asymptote here. What this is, in fact, we're not going to cover it on this course, but at x equal to minus 2, we're going to get a hole. There's going to be a little hole in the graph.
Sure, how did you get that minus?
So menu, graph entry mode, and change to relation instead of function. And this lets us put in a x equals type relation. So let's have a go at sketching this. Let's have a go at sketching this. We've got our vertical asymptote. We need to find our horizontal asymptote. So our horizontal asymptote, we should be able to see that y is equal to 3 over 1 is the horizontal asymptote. Our vertical asymptote is x equals minus 3. So to sketch, we draw our axes. We put in our asymptotes first. We have one asymptote at x equal to minus 3 and the other one at 3. Label these two. Y equals 3. X equals minus 3. So for the horizontal asymptote, it's always going to be the lead coefficients divided by each other if the exponents are the same. So looking at the shape of our curve, it goes through this point here. Goes through this point here. Our graph looks like this. And then up here it just looks like this. So this is how our curve should look. Sorry. Last question for today, exam style question. Let's take 5 minutes for this one. Yeah. Okay, so we have the function we have the function f here, and they've drawn it on the interval 0 to 5 only. And our first task is to draw it on the interval from negative 5 to 0. So we'll pull up our graphing calculator. I've entered it on the graphing calculator. I don't see it. Why don't I see it? Well, look at the scale here. This is going from minus 60 to 80. Let's adjust the scale on the graphing calculator so it matches the scale we want. This needs to be going from minus 60 here up to 80 here. This scale needs to start at negative 5. This needs to go up to 5. So I've adjusted the graph, the axis, so it looks the same as what we see on the graph, and we have to sketch this now. We can see that there's going to be a local minimum on the left-hand side there. So in order to sketch it accurately, let's start by finding that. We want to do analyze graph, find a minimum. I'm going to look either side of this. Oops, I missed. Let me try again. So I missed because I went too far over. So in my lower bound, I need to be a little bit more precise on this one. So I want to be in here, somewhere between here and here, a minimum of this. So I've got a minimum marked here. This is at a minus 1 comma 10-ish. Will do this for our sketch. So at minus 1 comma 10-ish, we have our minimum. We need to show our graph comes down like this and then goes up like that with an asymptote. So this is how it looks. Write down the, oh, I missed. Draw that again. I'm not happy with that. I want the minimum to be there, don't I? Okay. So write down the x-coordinate of the local minimum point. That's this one, minus 941, 797. So x-coordinate. Be careful here, I nearly wrote the coordinates. It's very specific in the question. It says x-coordinate, so x equals minus 0.941. So in question B now, I'm going to answer it here. Lesson B says, use your graphic to solve the equation f of x equals 20. So in order to solve this equation, so it's an equation system that we're solving, but we're going to be solving it graphically. So we press tab, we type in the new function which is 20. So we want y equals 20. We'll draw a horizontal line for us like this one. And we need to solve it. How many times does the red line cross the blue line? So how many solutions do we have? 3. So we want f of x equals 20 implies, and then x equals, I'm going to show you how you can quickly find all 3 this time. I'm going to go menu, analyze graph, find the intersection. I'm going to scroll over here for the lower bound and click, and then I'm going to scroll across until the first solution appears. There. Minus 2.45. So minus 2.45. Let me find the second one now. I haven't clicked on this one, so I'm just going to keep scrolling across until it finds the second one. There. It's finding the second one now at minus 2.52. Minus 0.252. 0.252. And I'll keep scrolling across and let's see if I'll find the third one. No, it's not. It's not going to play. So to find the third one now, I'm just going to have to go over here, analyze graph, find the intersection, put my lower bound in here, upper bound there. This one is at 2.70. Remember that this calculator will round off the zeros at the end. So we have 3 solutions there. our last thing, what is the equation for the vertical asymptote? So when we talked about vertical asymptotes on the last couple of pages, I said to take the denominator and set it equal to 0, and this will tell you where the asymptotes occur. So here on this one, we have a different expression, but the reason we're taking the denominator and setting it equal to 0 is because you can't divide by 0. Division by 0 is what's causing the problems, and it causes the vertical asymptote. So likewise in this equation, you can't divide by 0. So if we were to put 0 in, that last term, 5 divided by 0, would cause a problem. And that is what will cause the vertical asymptote. So the vertical asymptote is going to be at x equals 0. That's the last question. Okay. So that's it for today's lecture, but what I'd like to talk about is the homework. Our homework today is going to be on cognitive. So you'll find you can go into your cognitive, you have an assignment that is appearing, you have a link for it which is appearing, and it should take you in. And it will look like this. When you go into the assignment, it's a reading assignment, so you have to read through. It's going to talk about a lot of the things we talked about in today's class. You've got some hyperlinks that you can click on or float over, and then there's some apps that you play with that show you where things are going. And most importantly, it comes to the questions. So the homework questions is not in the textbook today, it's in the cognitive. So you have this one, for example, is a question that you're asked to do, and it shows you to find the local minimum and maximum points. If you don't know how to do it, depending which calculator you have, most of us have this calculator, you can click on the step-by-step instructions of how you use the calculator. And then when it comes to the questions, so it's these examples that I want you to do for each section. Have a go at doing the question yourself, and when you've done it, you can click show solution, and then compare your answer to the answer you're supposed to achieve. When you've done it, click that you have completed the assignment, and that's it for the homework.